Okay, let's begin here. Sorry. So today we're going to finish cluster analysis. Unfortunately, we were right in the middle of an example. Last time we just had to stop because we run out of time. So we'll quickly finish that. We'll start a new topic, discriminant analysis today. And also remember that project number 2 is due on Friday at 5 p.m. Are there any questions before we get started here? Okay. So we were talking about the goblet data, k-means clustering, and we basically had come to a point where we looked at a plot of W versus K for the number of clusters, and we thought, okay, 5 clusters might be something to look at. Is there a problem?
Yeah.
And you might remember us talking about a particular program or function from a program called pca.ca.plot2, which basically allows us to plot the principal component scores. And depending upon when or if you've downloaded this program, there was one small component to it that I changed about a week ago. So in the program itself, right now, so here's my function. To open up a new graphics window, because there's a number of plots being produced, I use dev.new, which stands for device new. We've seen an example of that way back in the introduction to R notes. And what was there previously was win.graph, which does exactly the same thing. It opens up a plotting window if you're using a Windows-based computer. So if you're not using a Windows-based computer, you will get an error message. Now again, I updated this. I found this issue about a week ago, and I uploaded a new program to my website. But if you had already downloaded it, then you might have that win.graph issue. So just simply find win.graph and replace with dev.new. Very small thing. Okay. So, it wasn't a clear cut here for choosing 5 clusters. And when we use this plotting function that I created, here's the plots that we were looking at last time that helps us illustrate, where the 5 clusters are. So, if we just simply look at where the plotting points are, or the different plotting points, here's my corresponding clusters. And, especially for, let's say, this cluster and this cluster, it's not necessarily totally clear that they should be separated. So maybe, now from looking at this plot, maybe 4 clusters might be better. And so if we take a closer look at another plot, so, my program doesn't, or my function doesn't automatically do this. So you would have to do a parallel coordinates plot on your own using standard code that we've used before. And here's a plot of the data for where the color corresponds to the cluster. And we can see definitely for the black lines there, they stick out from all the other lines there. And so that makes sense. The black makes sense. These are large overall goblets. The green also stick out. So the green kind of matches what the black is doing for W1 and W2, which is towards the cup of the goblet. But once we get to the base of the goblet, which is the other variables, we see the green go down. So we see the differences between the black and the green. So definitely the green, the black, I'm comfortable with. The problem that we were mentioning last time was, take a look at the 2 blues in the red. There's quite a lot of overlap. It's questionable then, should these be separate clusters? Now, there is some justification for the light blue, the cyan color. Notice how, how those stick out from the blues and the reds. These stick out from the blues and the reds. Not much, Because, obviously we see some dark blue that was fairly close to the cyan. But even here, it kind of sticks out, except for there's a little bit of an overlap. So maybe I could justify the cyan. And let's again take a look at that with respect to this plot here. I use exactly the same colors, and you can see where the two blues are and where the two reds are. Why, why it might be questionable to actually separate them out. But if I had to, definitely I could see, the cyan. In terms of all those three clusters, the cyan is maybe a little bit different from the dark blue and the red. But we do see that dark blue and the red there. It's like, well, why are we making the dividing line? Why are we drawing this dividing line there? Why? It's questionable. So maybe 4 clusters should be better. And so this gets into an overall point that I tried to mention last time, but I want to mention here again, is that you can use this plot of W versus K as basically a starting point for how many clusters you should use. But to fully justify how many clusters you're going to use, you need to look at like the parallel coordinates plots. You need to look at the PCA score plots. And from that, combined with the plot of W versus K, you make an overall judgment. We can see here that there could be, let's say, multiple justifiable number of clusters. I think that is actually the case here. But, especially like for your project and eventually for a test, you need to go through the entire process to come to a conclusion. As long as you go through the entire process, you'll be fine. So I urge you then, on your own, to modify my code then to see what happens when you have a different number of clusters. Does it make sense? What happens if I go down to, in this case, I have an example here with 3. Notice what happens when I have 3. Okay. I can see the black standing out from the other ones. Okay. I can see most of the red standing out from the green, but notice how everything there was combined together. But at least from looking at that plot of W versus K, it would be hard to say, okay, at 3, that's where that plot starts leveling off. And therefore I should use 3. I couldn't say that. And again, so that plot of W versus K gives you a starting spot to go from. You just have to be careful with over-relying on it. Let's see here. So here's the parallel coordinates plot for 3 as well. And you can see how the black stands out. The green for some of the variables. Let me actually get the variables on there. The green is somewhat different. Look how green, look at W1, how the green mostly stands out from the red. There's a slight overlap. Some parts of W6, the green definitely stands out from the red. So that's why we're coming to this like, well, okay, yes, I do see some differences, but maybe they're not great differences. And we need to make a decision. Well, what should I do? And maybe multiple justifiable options are. There could be multiple justifiable options. Let's see here. One last thing I wanted to ask you. So it might be interesting on these plots for the principal component scores to draw where the cluster means are. With K means clustering, we're going to have K means one, let's say, mean vector for each cluster. And it might be interesting on a plot like this to actually show where the cluster means are. What would you do first to do that? This gets into understanding principal component analysis. How can I show the cluster means? So here are the cluster means right there. What's that?
Research centers in the K-means in the available components. Three centers. Is that the mean?
Well, the mean is kind of meant to be, the center. I mean, a mean is not a perfect measure of centrality. But yes, it's supposed to be a center. But how can I get the exact location of, let's say, this plotted on my principal component score plot? Well, if I know my principal components, the actual equation, what do? I just stick in for W1, 1.54, for W2, 1.56, and so on, and I find the score for that. And then I could plot where that's located. Do that for principal component 1, do that for principal component number 2. Now I know where that center that will be located. In terms of R, how would you actually implement it? Well, you need a data frame that has this stuff in it. The k-means, you can actually pull it out of this object right there. Then you can use the predict function associated with printcomp to actually automatically do the math for you to find those scores. And so that's how you would do it. I have not done that, but it will be interesting to see where that mean is located. So anyway, I wanted to bring that up because it's kind of just getting into the whole idea of understanding principal component analysis, and that how would you find scores for something that's not actually in your data, that's automatically calculated for you from printcomp and from predict. Yes?
Still again about means. Related to
well, to do k-means clustering, each cluster has a mean. Okay? We then after we do k-means clustering and choose a number of clusters, then we use principal component analysis to visualize the clusters to try to make sense of them. And so it would be interesting then to see where the cluster means are located relative to a PC number 1 scale and a PC number 2 scale. Okay? Any other questions? Okay, next we're going to go to discriminant analysis. And just to set the stage here, let's take a look at my course website here. If you remember, I basically have broken up the topics for our course into 3 different sections. We have now just finished section 2, and we're going to go to section 3, called prediction. And what this basically means is that now we're going to observe data where each observation has a group associated with it. And we actually observe what that group is. And what we like to be able to do is something similar to what you would do in, let's say, regression analysis. We have a set of independent variables or explanatory variables, and we're trying to predict what group a particular observation falls in. The key is, and the difference between this and cluster analysis, is that now we know what the actual group is. There are a wide variety of number of ways to do this prediction. I've chosen about 4 to 5 different ways that we're going to look at in this particular course. And as you might imagine, not one method is always best. So if there was, then we would just do one method and move on. And so we'll talk about a number of different methods here. They have advantages and disadvantages. You'll see that as we go along. And there's many more other methods out there. Again, you could do a whole course on just this topic or this section. Okay. So typically, when one does a multivariate course, you start with this method called discriminant analysis. Let me change some of the zooming. So I would say that this is the most traditional method to use. It does have some assumptions behind it, but it's, in a statistical sense, it's often what's called robust to those assumptions, meaning even though you, in this case, we're going to have to make a multivariate normal distribution assumption for our data, these methods still often work very well, even if that assumption is violated. And so here's the setup. Suppose we have capital N observations once again, and each observation comes from a particular group where we have capital K groups, and we know what those are to begin with. When one teaches this, you will often see people refer to the groups as populations, because you can kind of think of, okay, these observations were maybe sampled from that population, these observations were sampled from that population, these observations sampled from that population, and I want to develop some kind of statistical technique that allows me to predict, does this observation come from this population, this population, or this population? And once I have that technique, then I can apply it to a new situation, a new data, a new data set where maybe you don't know what those groups, those populations are. And so to help you understand this better in terms of what we're going to be doing, here are actual 3 places where I've applied discriminant analysis and some of these other prediction methods as well during my career. The first one is a situation we already have some background with, and that is with the place kicking data. So in football, you can have a success or failure. Those are my 2 groups. That's capital K is equal to 2. Each place kick is either a success or a failure. And you might think that there are some independent variables, explanatory variables that affect, is this going to be a success? Is this going to be a failure? For example, the distance of the place kick, the wind, some measurement of pressure that a place kicker has upon them. And so then, what I have is I actually have a sample of over 1,500 place kicks. And I like to be able to develop a statistical method. We often refer to these as rules that says, given that this is a distance of, let's say, 30 yards, it's windy, there's lots of pressure, I'm going to predict that observation to be a success. I like to be able to, or failure. And so then, with this statistical rule, we'll want to evaluate how good is it. It's probably not going to get everything right in terms of our original data. How good is it? Because if it's good, then what I can do, I can go give it to, let's say, the Kansas City Chiefs. And, you can imagine the coaches on the sideline in R, and they plug in, okay, this place kicker has a 35-yard place kick. What does Chris say for, is this going to be a success or failure? And this will help me make a judgment. Should I actually kick the field goal or maybe do something else? Okay. Another problem that I've worked on deals with weak kernels. This was actually a consulting problem where a grain scientist came to me and another person for help on it. I don't do much consulting, but this is part of my job. But this was one time where I did do it. And so what this particular researcher was interested in understanding was, could they develop an automated method that, well, let's say, look at a weak kernel and tell them, is this a good kernel? Is it healthy? Or is it maybe a sprout kernel? Meaning that maybe, these kernels are seeds. Maybe, it has actually a little sprouted. Or is it maybe a scab kernel? Meaning it's actually diseased. They want to automatically, basically, send some kernels through this process and have it automated so that they can say, okay, this kernel is good, this kernel is, it's okay, this kernel is not good. And that would then lead them to deciding, well, what are they going to do with the kernels? And so what this researcher did was they took a sample of about, I think it was like 250 or so, maybe 300 kernels. And they actually had someone visually inspect each single kernel to make a decision. Is it healthy, sprout, or scab? Then they sent this kernel through their automated process that would measure the density, the hardness, the size, the weight, and the moisture content. And so those are my, let's say, independent variables. And so based upon these independent variables and knowing what someone has judged to be healthy, sprout, or scab, I want to come up with a statistical method, a rule, to decide, okay, just based upon these measurements, that is going to be a healthy, or that's going to be a scab kernel. And the last one was I was working with some people at a government, at a Department of Energy lab. And I was working with a few engineers. And they wanted, and what at this lab, the Army had come to them and they say, okay, imagine a scenario where you're on a battlefield, unfortunately, and you have some unexploded artillery shells. It would be of interest to determine, well, what's inside there? Is it going to be blow up, in terms of some kind of explosive power, or maybe it's actually poison gas inside of there, or perhaps it's empty. And so they wanted to figure out, is there a way that we could make that determination, but without actually touching the artillery shell? And so what they were trying to do was bounce some sound waves off the artillery shell, and based upon the readings that came back, they were hoping to use these readings as independent variables to help determine, well, is it poison gas that's in there or not? And I was actually at a very beginning of this process. And so we weren't actually using artillery shells at that time. Instead, we were actually, if you've heard of, Sunny D juice, and, you can imagine, I don't know why I didn't bring my container here. So they let me keep one of their containers. But you can imagine, let's say, a small container of, let's say, like orange juice. Okay? And they had like 40 of them. And 10 of them, they kept with having orange juice in there. Another 10, they poured out the orange juice and put water in there. Another 10, they put sand in there. And another 10, they left empty. And so what they wanted to do was, based upon their mechanism of bouncing sound waves, they wanted to see, could we first do in this simple setting, determine what's inside these Sunny D juice containers. And so again, one of the methods that we used was discriminant analysis for that. And so as I said before, this is somewhat similar to what regression analysis gives us. We have explanatory variables. We're trying to predict a dependent variable, a response variable. But the response variable in that particular case for regression would be like you can think of it like continuous. So for example, going back to our GPA data set, I have high school GPA and I'm trying to predict a student's college GPA. The college GPA is a continuous measurement, you can kind of say. Here though, our dependent variable is a grouping. It's a group variable. So it's like a categorical, a qualitative variable. Okay. So let's begin by thinking of a simple scenario where we have just two groups or two populations. I'll use both terms together. So our data comes from two populations, two groups. And we're going to assume that our data comes from populations that can be characterized by a multivariate normal distribution. And maybe I shouldn't have done this, but I'll say, let's say population 1 is just simply denoted by capital Pi 1. Population 2 is denoted by capital Pi 2. And so that means population 1 looks like this, where it has a particular mean. Let me actually turn off my spell checker here. So population 1 has a particular mean vector in a particular covariance matrix. Population 2 has a particular mean vector and covariance matrix as well. We could be measuring p different variables in each population, or we are measuring. So that means that our x here, let's say a random vector, is going to be p by 1, and this would contain, let's say, our observed values eventually for one particular observation. And our goal is to develop a method called, or to use discriminant analysis to be able to predict, does X actually come from population 1 or population 2? Should it be group 1, group 2? And there's 4 different ways that one can think about this, where this first way is the most general. It's called the likelihood rule. We talked about maximum likelihood estimation before. Remember, with a likelihood function, where we're trying to find a maximum likelihood estimate, we look at what value of our parameter makes that likelihood function as large as possible. That value then corresponds to the most plausible value for that parameter, and thus what we call our maximum likelihood estimate. And so we are often very interested in a large likelihood function. And so what we could do here is, let's say we do observe X. We could form 2 different likelihood functions. And since we only have one observation here, our likelihood function is very simple. We just write out the multivariate normal. So notice how I have a 1 here, I have a 1 here, 1 here, 1 here. That's just a regular old multivariate normal distribution. That ends up being our likelihood function. So we have one for population 1, we have one for population 2, and in both cases, we're just putting X in there, which will be, let's say, numerical values. You can think of our mu1. Let's say somehow we know what mu1 is. We put that in there. Somehow we know sigma 1. We put that in there. And so simply then, since we really like having as large of a likelihood function as possible, we could say X should be put into group 1 or population 1 if the likelihood function for group 1 is larger than it is for group 2. Okay? Simple. That's it. Now, of all these 4 rules, this is maybe the most complicated, and we'll actually end up spending the least time on it, but I do want to at least put it out there that this other rule, this other approach exists. Let's say that our covariance matrices are equal to one another. So in other words, this is equal to this is equal to that. That ends up simplifying things for us. And it simplifies it in a way that we can now, instead of looking at the full likelihood function, we can say, okay, let's choose population 1 if this B vector, which is formed in this way, transpose it times X, subtract off this K calculation. If that's greater than 0, choose population 1. If it's not, choose population number 2. So the key is, well, how does this B come about? How does this K come about? And if you, let's see if I can get this on one screen here. And if you look at the likelihood function and you compare it to what B and K have, what B contains and what K contains, you can see some similarities. You know, you see a mu1, you see a mu2, you see a sigma matrix. And so if you could go through the mathematical details, and you're not responsible for it, but you could go through the mathematical details and you could say, and you could show that using this, now with the covariance matrices being equal, leads to a little bit more of a simplified rule. Okay. Now, the main reason why I still at least briefly mention this version here in a class like this is that we're using discriminant analysis. In particular, right now, even though I haven't introduced it, we're using something called linear discriminant analysis. Where does the word linear comes from? Well, simply, we are taking a linear combination of our x's. And so what you're going to see later on, there's going to be something called quadratic discriminant analysis. Or now, essentially, the x's end up having some squared components to it. And so, in the end, there's going to be two different ways to apply discriminant analysis, essentially. Linear or quadratic. And so this is called a linear discriminant rule. We just talked about the linear part. The word discriminant, where that comes from is that I am trying to discriminate between observations coming from this population or that population. Obviously, the word discrimination is not good, I mean, in other contexts, but that's why this word is being used. People are using it as a way to tell apart observations from different populations. Okay. So next, I think, so here's the rule 3, or the third way to do this. I think this is the most intuitive, especially given what we just got done doing with cluster analysis. And that is, I can apply what's called the Mahalanobis distance rule. Mahalanobis, it was a famous statistician from India. And let's start off again with assuming the covariance matrices are equal to one another. Then that likelihood rule then becomes equivalent to this. How about for x, I look at how far it is from the mean for group I. So it could be group 1, it could be group 2. I do the same thing here. And notice if we just look at that and ignore sigma for now, notice how that's very similar to Euclidean distance. But now we're looking at how far x is from mu, rather than how far, let's say, one observation is from another. Now we know, though, that our data, our x's, will have different variances. The variables will be related to one another in certain ways. So how about we take that into account by now, in the middle, putting in sigma inverse. And so what we have here is just a different way of measuring distance, that x is from, let's say, the center of population 1. X is from the center of population number 2, where we take into account the covariance matrix. So we have then, let's say, D1 and we have D2 if we have two populations. So what population or which group should I classify this observation into? Well, the one that has the smallest distance. It says it's the closest. That's how it works. And so you would need to do this calculation then throughout your entire data set. Now let's say, instead of having just two groups, suppose we have 3. Well, what do you think you would do? Well, you calculate 3 distances for x, and you put x into the corresponding, or you predict the corresponding group that has the smallest distance. Well, what happens if you have 4 populations? You do the same thing. So the extension is fairly easy. And so here's just a little bit of a diagram that shows essentially what's going on. So you see these little ellipses there. That's just meant to be, let's say, a contour, because we're still assuming that we have 2 multivariate normal distributions. And so suppose that this is one contour of that distribution. And it's the same contour in this case and in this case. And so if I were to just have x being, let's say, with 2 variables in it, we can see that x here is closest to population 1. That's essentially what we're doing. This plot, though, doesn't necessarily take into account that covariance matrix.
What if the covariance is not, the sigma is not the same? Or
we will look at how this is modified then. Basically, we're going to modify that distance. So right now, I'm trying to be simple, and we're going to assume that we have equal covariance matrices. But yeah, that's a good point. Then the last one is what's called posterior probability rule. And this is equivalent to the other three as well, as long as the covariance matrix is the same for the two groups. And this is how it works. The posterior probability is the probability that that X is in population, let's say I, or comes from population I. Here's how that probability is calculated. You take your distance that you just had for population I, you do a little bit of a mathematical transformation of it, and you divide by the distance from population 1 or group 1, and the distance for population 2 or group 2, where again we do that same mathematical transformation. And so all we're doing is just kind of taking into account these distances, rescaling it to a value between 0 and 1. Just to give you a more of an intuitive feel for why this works, let's say that we have two distances, 5 and 10. This is not in the notes. I have two distances, 5 and 10, where the distance to group 1 is 5. Well, then I would classify that particular observation into group 1, because the distance is smaller. Well, what if you actually then did this calculation that I just presented? Well, for group 1, I get a posterior probability of 0.92. For group 2, I get a posterior probability of 0.0758. And so we can see that this posterior probability is greater than this probability, so therefore I'm going to classify that particular observation into group 1. And so all it is a way to do the rescaling to a more comfortable scale. Again, imagine if you had 3 populations instead. What would you do? Well, you just add in the third one, the third distance, with this little mathematical transformation. And again, you would choose then the particular group or population for the particular observation by looking at 3 posterior probabilities in the end and choose the corresponding group that has the highest posterior probability. And you can imagine, again, if I have 4 groups, 5 groups, how that equation just would be extended. Now, in the end, though, this is actually not a probability. Because there's no random event actually being considered here. X does either come from population 1 or 2 or 3, and we're essentially conditioning on what X is. And so there's not really a random event here. But the reason why it's called a posterior probability, 2 reasons. First of all, we are getting numbers between 0 and 1. The word posterior comes about, and you'll see this in other places in statistics. This is often really used with respect to what's called Bayesian methods in statistics, where we condition on our data, and then we look at corresponding probabilities associated with parameters. And since we're conditioning on that data there, that's where posterior comes about. I'm doing post my sample. What are my probabilities? And so that gives you just a little bit of a background in terms of why we are calling it that. Now, of course, all these rules rely on knowing what mu1, mu2, and sigma are, and perhaps sigma 1 and sigma 2. In reality, you're not going to know those. Those are population quantities. So what are you going to do? Well, you're going to estimate them. So you plug in the estimates, and then you proceed. Well, what do you do then with respect to the estimate of the covariance matrix? Well, we can apply something that you would see in a Stat 801 course. If you remember, when you did a test like this, these are not vectors. It just represents 2 different means. When you did a test for the difference of 2 means, or in other words, are the 2 means equal to one another? you would find a quantity, or at least one way to do it, would find a quantity that looks like this, which was the pooled estimate of the variance of your sample means. This is often standard notation. Maybe you have not seen it, or maybe you haven't seen this notation before, but you've at least come across it. You should have. And what you would do is something like this. You take your sample size, let's say from population 1, let's call it little n1. And you do n1 minus 1. And then you find the sample variance for corresponding to the sample 1. You do something similar for sample 2. And you take this over n1 plus n2 minus 2. Does that look familiar? Hopefully. Well, if it does, then the multivariate extension of this is right here, where this is how we could estimate then the corresponding assumed equal covariance matrix. Now we just do it in a multivariate stance or setting. If you by chance want to see what this is in a Stat 801 course, we can go to my 801 notes here. I'll point it out to you exactly where. Let's see here. Inference for 2 means, independent means 1. And that's where you'll see the univariate, it's often referred to as formula for that. Okay, so this question here, we've been talking about how, suppose there were more than 2 populations, how would these rules be adapted? This wasn't originally in the notes, and so that's why in this particular case I colored it in red, but we've been talking about that throughout. Okay, so we have 4 different ways that are essentially are equivalent if the covariance matrices are equal. 4 different ways to develop a statistical rule, statistical method to say this observation goes for group 1 or group 2. Now you would like to be able to figure out, well, how good is this rule? How good is this method? And so what we want to do is understand, if, let's say, that a particular observation comes from population 1, I want to know then what's the probability that I'll get it right, that I will classify that observation into population 1 or group 1. But also I want to know how often will I get it wrong? How often will I misclassify it? And so we're interested in measures of accuracy here. Or conversely, you could say interested in, let's say, probabilities of misclassification. And so once we develop a rule then, we need to try it out. By far, the best way to get a measurement of your accuracy is to, let's say, go out and collect some new data. So like with respect to the place-kicking data set, what I could do is I have 1 season's worth of data. How about we try it out on the next season? Okay. With respect to the wheat data, I have a sample of, let's say, 250 kernels. How about I go take out another 250 kernels maybe and apply that method to classify the observations and see how well it does. The problem, what is the problem with that method, though? By far, it will give you the best measures of accuracy. But what's the problem with doing that in actual application? Yeah, it's going to cost money to take another sample, right, depending upon what the data corresponds to. It's going to take more time. And so because of that, depending upon the situation, this might not actually be applied. But this is the best approach. So what is frequently done is to, what I have here called, develop what's called a holdout data set. I don't know if I like that wording anymore. But imagine, let's say you get your observations. And before you develop a rule, a statistical method to determine group 1 or group 2, you split your data into 2 parts. You take this part over here and you develop your rule based upon it. What that means for us with these methods is I'm going to find the estimated mean vectors. I'm going to find the estimated covariance matrix. I get my rule, and then I try that rule out on this data that I had set aside. How well it does there in terms of accuracy is then what I would actually, let's say, report regarding, like maybe if I was doing a paper, that I would report to measure how good this statistical method performed. So very frequently, you'll hear people refer to these two data sets as follows. This data set that you're using to develop your statistical method, your rule upon, is often referred to as a training data set. It could be also referred to as a model building data set. The data that you try out your method on is often referred to as a validation data set, a calibration data set, a test data set. Is there any other ones? There might be one other name. Those are names that I'm throwing those names out there because I wouldn't be surprised if you come across those before. So what's the problem, though, with this method, though?
You need a big data.
Yeah, you need big data to do this work, to do this. So, imagine a situation where you had 100 observations and you divide it equally, 50 observations here, 50 observations here. Now, from your past statistical experience, you know that the more data you have, the more you understand your problem. But now, you basically have reduced your amount of data to come up with this rule in half. If I only had 100 observations to begin with, maybe it might not work as well. So I'm taking out half. Now, if you do have a big data set, let's say you have 1 million observations, maybe that detrimental aspect of dividing the data up will not be as severe. And still, you would expect you're probably going to lose at least a little bit, even if you have 1 million observations. So, in the end, that's something to think about with respect to this. Another way to measure error, or the accuracy, is what's called the resubstitution method. Meaning, I have a data set, let's say of 100 observations. I develop a rule, a statistical method based upon it that classifies the observations into the groups. And then I try out this rule, this method, on the exact same data. What do you think is a potential problem with doing that? Bias, exactly. Because that statistical method has been optimized for this 100 observations. And now you're going to try it out on the exact same observations. So that is a potential problem with that. And then lastly, and so typically I only will use resubstitution when I'm trying to, let's say, initially demonstrate some of these actual calculations to you. But in actual practice, I might look at it, what the results from resubstitution are, but I will not make a final judgment based upon that. Lastly, something called cross-validation as a way to come up with these accuracies. This is how it works. And there's a number of different ways to do this. We're just going to simply focus on one to help keep our focus. Suppose you have 100 observations. How about you temporarily remove observation 1 from the data set, you develop your statistical method based upon that, and then you try to classify that one observation. And then you record, okay, did I get it right, that classification or that grouping, or did I get it wrong? Then I put observation number 1 back in the data set, and then I take out observation number 2. I develop a new statistical method, new statistical rule based upon the remaining 99 observations. I try to do exactly the same thing. I try to classify or predict the grouping for observation 2. I do that for all 100 observations. I look at then the overall accuracy with respect to those 100 different predictions. That's what cross-validation is. This is often referred to as a leave one out method. There's other ways. Let's say maybe if you have 100 observations, maybe leave 10 out and do it on 90. Then put those 10 back in and take out another 10 out. Do it on the remaining 90 and so on. We'll just focus on leave one out. In statistics also we often refer to as what's called jackknifing. One of the few times that we have an interesting name for stuff. So what's the problem with this particular method?
If your sample size is very small, when you remove some samples, they actually not distribute.
Yeah, I guess that would be one thing. That wasn't what I was thinking about. Let's say if you have a sample size of 10. That one observation is 10% of your data. But what potentially could be another problem with this? Let's say I had 1 million observations.
Some outlier you may choose.
I wouldn't say outlier. I don't think that's, well, I guess with any statistical method, if you have an outlier, that might cause an issue, yes. But I'm looking for, if I have 1 million observations, how many different rules or methods, how many different rules am I going to have to find? 1 million. And so it could take a lot of time. Okay. Now, in the end, though, what would you report as, let's say if you're writing a paper, what would you report as the actual statistical rule? Well, you would still use, let's say if you have 100 observations, you would do all 100 observations, and you will report then what you get from that as your statistical rule. You're only doing this cross-validation as a way to measure how good the rule is, because you don't have maybe access to a holdout data set or validation data set. You don't have a good way of taking another sample and so on. Now, cross-validation does have some bias in it, but it's not going to be as much as what you have for resubstitution. What you typically see done most in practice is cross-validation, and then also use the holdout data, where you have a training and validation. Okay, so let's apply some of these methods to the place kicking data. One thing that I want to point out is that with this place kicking data, let's see. Okay, I guess I don't talk about that yet. So I'm referring here to the training data. I've just ended up using a different name, the model building data. That's going to end up having 83% of my observations. Validation data is going to have 17% of the observations. What do you typically see in practice in terms of how you do the split, in terms of the percentage of data in one data, percentage of the overall data in another data? You typically see in practice, on one extreme, you'll see a 50-50 split, or 50% of the observations go here, 50% go over here. And it might go down to, let's say, 80% for your training, 20% for your validation. Without getting into what I did wrong here, I ended up doing 83 and 17. In the end, it's not that big of a deal. It's close to 80-20. But you can imagine, and there's not a set rule here, but you can imagine, okay, if I use an 80% for my model building or training, I might potentially be able to develop a better rule than if I were to use 50%. And so there isn't a strict a way to go about doing this. Towards the end of these notes, I will actually show the actual R process to split a data set. For now, let's just say that I do have two data sets. One's called placekick.csv, which is going to be my model building or training, and valid.csv. It's a comma delimited file that has my validation or my test data set. Okay. Now, with this, here's what the data looks like. So a distance of the place kick change is a binary variable for if the kick is successful, will it cause a lead change in the game? So let's say if the score was the kicking team has somehow they have 8 points and the team that's playing defense has 10 points. A successful field goal would then cause the score to change from 8 to 10 to 11 to 10. So there's a lead change. And so this could be one way to measure pressure, for example. And maybe that place kicker, knowing that, oh, now my team's going to start winning the game, maybe that gives you pressure. So elapsed 30 is the number of minutes elapsed remaining, elapsed in the half. Again, that might be a measurement of pressure as well, because once you get down to about 0, what that would mean is that the place kick would be done like maybe right at the end of a game, maybe perhaps. PAT is a 1 or 0, 1 for field goal, 0 for a point after touchdown. Field goals are worth 3 points. Point after touchdowns are worth 1 point. Type corresponds to the stadium type. 1 is for an outdoor stadium. 0 is for dome. At the time when I collected this data, actually there were not retractable roof stadiums. Field is a 1 for grass, 0 for artificial turf. Wind is a 0 for not windy, 1 for windy. And good is our grouping variable. 1 for the kick was a success, 0 if it was a failure. Okay, now with discriminant analysis, we have to make an assumption about, we have to basically assume multivariate normality. Is this violated here? Is this assumption violated? So let's think about let's just think of like a regular normal distribution for one variable. The variable is a continuous variable. Let's say if it was a standard normal, somewhere between about -3 and +3. But the key is it would be continuous. Do I have continuous variables? Okay, yeah, I have a number of binary variables here. And so the multivariate normal distribution here, assumption is violated. Just because it's violated doesn't mean you should throw this out. Because as I was saying earlier, discriminant analysis can be quite robust to non-normality. And so in actual application, what I would actually do is, let's say, apply discriminant analysis, apply maybe a few other techniques that we will eventually get to this semester, and determine, okay, which does best. And then that would be the method that I would go with. So the main function R that does linear discriminant analysis is called LDA. It is in the package called mass. We've seen the mass package before. So for example, that's where the parallel coordinate plot function came from. So now that, yes?
So the variables need to be continuous or be grouping?
Well, at the very least, they need to be continuous, except for the grouping variable, because it has to be categorical. You're group 1 or group 2 or whatever. In this case, it's actually group 1 and group 0. So yeah, the independent variables would have to be continuous and also exhibit a multivariate normal distribution. If I were to satisfy all the corresponding assumptions. That's not the case here. So now that I have this data, though, it would be interesting to apply some of the techniques that we talked about earlier in this course to explore it first and maybe get some idea about how well do we think linear discriminant analysis will work. So what I did was I used principal component analysis to start. I'm not going to go through the code here because it's the kind of methods that we've seen before. Notice here, it takes at least 5 principal components to get up to 80% of the total variability explained in the data. Also, there are 4 eigenvalues, estimated eigenvalues that are greater than 1. So what this is saying, maybe 4 or 5 principal components are needed. But we can still look at it in terms of just 2 principal components and 3 principal components so that we can view our data, just understand that we might be missing some information. So here are some plots of the principal component scores. So PC number 1 is on the, let me make this a little bit smaller. PC number 1 is on the x-axis like usual. PC number 2 is on the y-axis. I have the plotting point corresponding to the good variable, where, and I don't know why I didn't do this, the black represents success. I'm sorry. The black represents a failure. Let me just double check that. The red represents a success. The black represents a failure. In this data set, and this is going to be important coming up at some point, maybe not today, we have many more successes than what we have for failures. And we will need to take that into account at some point. So, why? So it looks like we have 3 distinct sets of observations. And even within them, we have some distinct sets. Why do you think that occurs? What characteristic of this data do you think is causing that? It's because we have these variables that are simply binary. We have discrete variables. And so that's why we see a plot like this. This is not something to be alarmed about. But I just want to tell you, because we hadn't really seen a plot like this before for principal component scores, where we have this clumping of these observations. And so, for example, I'll skip ahead here. Here's a principal component score plot where the plotting point now corresponds to the PAT variable. So it's either a PAT or a field goal. Here's another plot corresponding to where the plotting point corresponds to the field variable. Now, you might be wondering, okay, I would have expected maybe to see 2 clumpings of the points rather than 3. Why does this occur? Well, the reason being is because, at least in the NFL at this time, there were no retractable roof stadiums. So you could have artificial turf outdoors or indoors, but you always had to have grass outdoors. And so that's what that ends up corresponding to. Okay, let's go back up here. So we see the reds really mixed in with the blacks. The blacks tend to be, it seems like there's more blacks. I don't know how well you can see this there, but there tends to be more blacks towards higher values of principal component number 1. Now, without going back to the output, I will tell you that principal component number 1 has a positive coefficient on distance. And so what this is showing us is as the distance increases, the likelihood of missing the field goal or having a failure occurs. Okay? So that's why that happens. But what I want you to focus on here is that we have lots of reds and blacks all mixed together. Let's say that all the reds and the blacks were totally separate from one another. Would that be a good thing if we wanted to develop a good rule? Yeah. You would expect the discriminant analysis method to work well. Here, though, we have the reds and the blacks mixed. And so you might be concerned that I'm going to have some misclassifications eventually because of this. And in fact, that's what will happen. So you could also look at a 3D scatter plot as well. Okay, so let's actually then do the computations. So again, the LDA function is inside the mask package. The formula argument for LDA works just like it does in the LM function when you're estimating a regression model. You put the grouping variable first, which would be kind of like the response variable or the dependent variable, good, tilde, and then you put in, separated by plus signs, the corresponding like independent or explanatory variables. I put in what my data set is. This is my model building or training data set. CV equal false, meaning I do not want cross-validation to be done. I'm only saying that for now, just so I can demonstrate some stuff to you. So what's going to end up happening is by default, R will do some resubstitution when it tries to predict the classifications. And then also I have an argument called prior. We'll talk about that more later on. But for right now, what you can see here is that basically I have a vector for prior. The first element's 1/2, the second element's 1/2. What this is going to correspond to is that I'm telling R that 50% of my observations are from population 1, 50 are from population 2. Or in this particular case, I have good equals 0, good equal 1. That is not the case, but we just need to start somewhere, and so that's why I'm just putting what that prior is there. We'll look at how we can change that later. So you can't use summary with the corresponding object that's produced from LDA. Instead, if you just type the object name itself, then you kind of get the equivalent to the summary. DA1 is where I decided to put everything in. For, in this case, discriminant analysis, this is my first try. If you looked at inside of DA1, you will see that it's actually a list that contains a lot of useful information. So some of the output that is produced here, so for example, we get the means for each of the variables corresponding to the two groupings, 0 and 1. So I can... also, we have something called the coefficients of linear discriminants. This isn't quite B prime X, but I'll say it's close to. Or I'm sorry, it's close to that B. It's not exactly. And I'll explain more about that shortly. So if I do names, DA1, I see some information about what information is actually available to me. Let's see here. There's not many method functions that are associated with LDA. There is one called predict that we would use that will allow me to determine should this be, in this case, a success or a failure. And in fact, that's what I do. So I say predict, object equal DA1. And what this is going to do is put all the results into an object called pred.resub, for the lack of a better name. Inside of this pred.resub, you see something called posterior. Here are my posterior probabilities. So for example, for observation 1, posterior probability that's in group 0, meaning the failures for the place kicks, that probability is 0.11. For the success, or group equal 1, we have 0.89. So therefore, I would classify this particular observation into group good equal 1. That's my prediction. Notice I use the word class. I did this before. I often use the word classification to mean prediction, because we are essentially classifying the observations. That's part of the prediction. And also inside of pred.resub, notice we have $class, and this automatically gives you those predictions. Okay. Let's talk about note number 3 here. So in the output, I pointed to something called coefficients of linear discriminants. It gives you something that's like B of this B prime X minus K, but it is not exactly that. This is the only I've used a number of different statistical software packages. This is the only one that I've ever seen that doesn't actually give you B and doesn't actually give you K. Instead, it gives you a rescaled version of B that also has some components of K in it. So in the end, if you were to take this vector, let's see, if you were to take this vector, multiply it by X, if that's greater than 0, you go into one, you have one prediction in terms of the grouping. If it's less than 0, you're predicting the other grouping. That's how this works. So it's kind of like what B prime X minus K does, but it's just a little bit different. And because of that, you will not be responsible for it, and that will be the very last time that I will ever bring it up. If you want to know more about it, you can take a look at that book. Okay, let's see here. This might be a good place to stop then. So let's take a look at what's next for our class. I have my normal office hours today. Project number 2 is due at 5 p.m. on Friday. Please email it to me. Next Tuesday, we'll continue with discriminant analysis. And then looking further ahead, of course, we have test number 3 at the end of this month. Are there any questions? Okay, that's all for today then.